So now that we have the mathematical skills to deal with acceleration as a vector, and we realize that there are two components to that acceleration vector, the tangential component and the normal component, we can use that for a particular trajectory. So I have the position function, the trajectory of an object, r of t equals t squared. So this would be position. I want to calculate the values required to fill in the table and use the results to draw conclusions about the motion along a trajectory. Okay, so I'm going to start off with the derivative. So the velocity would be the derivative of the position, which would be 1 and 2t. Wonderful. Then the speed, which I really need because speed is in the denominator for both components, for both the accelerational tangential component and the normal component of acceleration. So you can see the denominator for both of those is speed. Therefore, I need to be able to find the speed, which is the magnitude of my velocity. Oops, forgot that little vector there. All right, which is the square root of 1 squared plus 2t squared, which would be the square root of 1 plus 4t squared. This is speed. Well, that's already what I need right here. So this is the square root of 1 plus 4t squared. So I can use Maple, or I could just use my head, but I actually did it in Maple. Let me pull it up. So I defined there's the parabolic curve, there's the trajectory we're working with. Right there, I named it t squared. And then I've got my speed, I define it as for speed. And I'm telling it to evaluate that speed at -1, 0, and 1, and I have those values. Right? So it's the square root of 5, which is 2.236. So the square root of 5, which is 2.236. Then this is 1, and this is also the square root of 5, which is 2.236. All right, so I've already got the speeds filled in. Now I'm going to have to find the acceleration component in the tangential direction. To do that, I'm going to need first my acceleration vector. So the acceleration vector is, of course, the derivative of your velocity vector, which is the second derivative of your position vector, which would be 0 and 2. So that means to find my acceleration component in the tangential direction, the formula says take the velocity vector dot product with the acceleration vector and divide it by the speed. Okay, well, velocity is 1 and 2t. I will dot product that with 0 and 2, and I will divide it by my speed, which is the square root of 1 plus 4t squared. The dot product of these two is 4t, so it's 4t over the square root of 1 plus 4t squared. This is your accelerational component in the tangential direction. So I will put that right here in the table. Right there. And then I will have Maple do that. So, I mean, yes, I could do it, but that's what Maple's for. So I have my accelerational component defined right there. And then I told it to evaluate it at those particular values. And you can see it's giving me the exact value. And then I wanted a decimal approximation. Okay, so let me write those down. So this is -4 over the square root of 5, which was -1.788. This is 0. This is 4 over the square root of 5, which is +1.788. Okay, so we could actually go put these on the graph, which I've placed down below. I didn't do it for this fall 19 semester, but I will in future have a graph sitting here. So here you have -1, here you have +1, here you have 0, right? So those would be the points on the curve. As a matter of fact, I could put those in right here. So if you're looking for points on the curve, this one would be -1, 1. This one would be 0, 0. This would be 1, 1. I'm placing t equals -1 into my r of t equals 0 into my r of t, and so on. And that gives me the points on the curve. So I know that it's those 3 points. This is at t equals -1, that's t equals 0, that's t equals 1. So at t equals -1, the acceleration in the tangential direction is right here. Right? That's at at -1, which is -1.788. Right? And then over here, this has to be the same length. They should be the same length as each other because they're the same tangential component size. They're both 1.788. So this is AT of 1, and that's 1.788. Oops, had some issues with the paper there, but it's 1.788. And so these two pieces of that tangential vector should be the same because the tangential vector, of course, is a unit vector. And since these amounts, these scalars are the same size, then you're taking the same component of that tangent vector. All right, so my acceleration here is downward, negative. My acceleration over here is positive, climbing. All right, so we've got that. Now, oh, and 0, because at the very bottom of the trough, right, the bottom of this parabola shape, there is no acceleration at that moment, just for that instant. If you think about it, we used that fact way back in Calculus 1 to find critical values of a curve. So we used the fact that the second derivative is 0 at that spot, right, to find maxes and mins, that kind of thing, or the first derivative, sorry. So that kind of thing. Second derivative figures out concavity. Okay, so now let's go find the normal component. To do that, we're first going to have to find the cross product because that's part of the formula. So let's take a moment and find the cross product of my velocity vector and my acceleration vector. And this is actually going to be a very easy cross product. So the velocity vector, if you look here, it has only x and y. So you're thinking, how can I do this? Well, that means that the z component was 0. So you just put 0 in. It's fine. So 1, 2t, 0, 1, 2t. And then the acceleration was 0, 2. And then there was no z component, so just put 0 in. With that many zeros in this, that means that this is a very simple cross product. The only thing that works out, that's 0, that's 0, 2k. This one right here is the only one that works. Backwards it's 0, 0, 0. Right? So the only one that works is 2k. So 2k, which would be 0, 0, 2. That's my cross product. Okay, so then the normal vector, or the normal component of acceleration, would be the cross product of v with a divided by, the magnitude of the cross product divided by the speed. Okay, well, the magnitude of the cross product is the magnitude of 0, 0, 2. So that's 0 squared plus 0 squared plus 2 squared, which is really not worth the ink I just used because we all know that's going to be square root of 2 squared, which is 2. And then the denominator is what we already found. It's 1 plus 4t squared. It's the speed. Okay, so that means that my acceleration component in the normal direction will be 2 over the square root of 1 plus 4t squared. I guess I can box this and this and this. Those are the 3 pieces they asked us to find. The speed, the accelerational component in the tangent direction, and the accelerational component in the normal direction. So now I need to fill in that part of the table, and then I'm going to use that to draw the graphs. So over here, I'm going to put in 2 over the square root of 1 plus 4t squared. Okay, so I'm going to make Maple do that as per usual. Even for number crunching, Maple works. So I've got my acceleration component in the normal direction defined. And so there it is. And then I'm telling it to evaluate it at -1, and then I asked for a decimal approximation at 0 and at 1. and ask for a decimal approximation there also. Okay, so going back, that means that I want 2 over the square root of 5 here, which was 0.894. Maple automatically simplified or rationalized that, but you know, I don't need to bother. So it's 2 over the square root of 5, which is also 0.894. Okay, so what does this mean? Let's think about this. So if I'm here at -1, the normal component is like this. It's got to be smaller. It should be less than that blue one, because the blue one is 1.788. So this should only be 0.894. I've probably drawn it a little too large, but that's the normal component at -1. At 0, it's all normal vector. It goes all the way up to 2, right? Because there is no tangential component to acceleration there. And then over here, it's also 0.894. So I should also make it smaller on this side, like that. These two orange ones should be the same size, just like the two blue ones should be. That's just because this parabola is symmetric, and I picked -1 and 1. If I had picked 1 and like 2, they wouldn't have worked out that way. This one is a sub n at 1. This is 0.894, and so is this. So those two are the same size. All right. So what can we tell about the motion? So of course we're moving this way because it's a vector valued function. So we're moving this way along the curve. And as we move, right, when we get here, we have tangential acceleration going this direction, which is negative. And then we have a normal component because we're changing direction. So this blue one is changing in speed and the orange one is changing direction. When you get to here, right, there's no change in speed for just that instant, and it's all direction change, right? Oh, sorry, this was 2, right? So it's all direction change at that moment because you're completely changing your concavity, or not your concavity, but your direction. You were going down, and now you're going up. So at that split moment, you're really changing direction over. So that's the most amount you can have in the normal direction. The most amount of acceleration you have is right there. And you know this if you're on a ride that does it. Right there, you feel it, right? You feel it getting pulled, right? And then you start going back this way. You've changed direction now, so that's why this is positive. So your speed is going up, going that way, but your normal component is going across. And if you move along the curve, that tangential one, that's going to be how your acceleration works, and your normal one will get smaller and smaller.